now we'll go. Different bondings. So now we're going to talk about the three different kinds of bonds: metallic, ionic, and covalent. So, metallic, low electronegativity, high delta, high difference in electronegativity. So we're looking at two metals being brought together. So the two metal atoms, neither one really, or the two elements, I should say, neither one really wants their electrons, but neither one can really get rid of the electrons because the other one doesn't want it either. So what ends up happening is they share all of their valence electrons. Okay? And this is what you get. Okay, you see on the right here. Let's bring back the pointer. You get the core of the atom. That is the core that we talked about when talking about valence electrons. You have the nucleus and you have the core electrons. So you have these positive cores studded inside this sea of electrons. Okay, these are all the valence electrons that they don't really want. They share them across the entire structure of the metal. So this, in various ways, explains all of the various properties that we see with metals. Namely, first off, they are malleable or ductile. Malleable means that you can shape it. Ductile means you can draw it out into a wire. So think about it. What happens if you hit this structure with a hammer? These metal cores, they just shift. Okay, there's the bonds of the metallic bond are called non-directional. That is to say, they sort of point in all directions. They don't have any one direction that they point in. So there's nothing holding the atom in one specific spot. So you hit it with a hammer, they just blank, and they just shift within that sea of electrons. Not a problem. So for the metallic bond, the metal atoms are free to move around. I mean, obviously there are limits to that. You move them too far, the metal will break, right? But on the scale of, a few dozen, a few hundred atoms, a few million, hitting it with a hammer, you can dent a piece of metal pretty easily. The atoms are free to shift, free to move, free to change the shape of the metal because they move within that sea of electrons. Metals are conductive. Okay, electrical conduction. This is important. Okay, I'm going to go ahead, bring back up this thing right here. Electrical conduction. Conduction means the movement of charged particles. Okay, so whatever kind of electrical conduction you're talking about charged particles of some kind moving from one place to another. In the case of metals, those charged particles are these electrons here inside the sea of electrons. Okay. Those electrons, those valence electrons in the sea of electrons, they're free to move through the entire structure of the metal. So if you apply a voltage on one side and the other side, positive on this side, negative on this side, then the electrons will move away from the negative toward the positive. Not a problem. And that is why metals are conductive, because of the movement of those electrons. Metals are shiny. This one's a little bit more complicated. It has to do with the way atoms share their orbitals. We'll be talking about atoms sharing orbitals a bit more when we talk about how covalent compounds form their bonds. Just know that metal atoms, they share, and what you end up with is a whole bunch of empty orbitals available. Remember, if we were talking about hydrogen, then we would end up with the Balmer series, or just the fact that when an electron moves from a low N to a high N, it absorbs a specific amount of energy in the form of, that photon of light. And then when the electron falls back down, it releases the same amount of energy in the form of a photon of light of that particular color. Right? That's where we get the emission and absorption spectrum. With metals, you end up with basically an infinite number of orbitals. Well, practically speaking, infinite number of orbitals at all energies, so it can absorb and release light at all energies. So it does. And that's why metals are really, really good at reflecting light. Once you polish them up so it goes back out at the same angle that it came in, you get a mirror. And it's just because of the fact that they're sharing electrons in this particular way. And finally, they form alloys. Because, like I said, these cores, the metallic bond is really flexible. And it's just a matter of, can you fit an atom in between these two atoms? If you can, then great, you get an alloy. That's, for a while, that was how they made steel. It was just they would take a piece of iron, they would, scatter powdered carbon on there, in the form of, soot, charcoal, right? And then they would just fold the iron back over. The iron would have to be hot enough that you could bend it with a hammer easily, right? But then you would just fold it over and hammer it down so that you would literally be pounding the carbon into the structure of the steel. You just keep on, then you scatter more carbon on there, fold the iron over, scatter more carbon, fold the over, and just fold it over and over again. Sort of like you're mixing two things together inside of a mixing bowl. And that's how you got these beautiful patterns, these beautiful wave patterns on old steel, is because of the way they were forging them, folding them, folding them, folding them. Let's see, water steel, I think, is what we're looking for there. No, that I'm not interested in Pokemon or water bottles. Waves in steel? No, that's talking about sound waves. Okay, so I can't find it with a quick Google search, so I'll stop trying. All right. Point is, for older metals, forged metals, by hitting it with a hammer, you could see those beautiful, beautiful patterns within the material of the metal from the fact that they were folded hundreds or thousands of times that way. And that's how you literally just forced the carbon into the structure of the steel, by hitting it with a hammer. All right, so a lot of alloy chemistry, semiconductor and metal alloys, is just about geometry. Can atom A fit within structure B? It's really interesting stuff. Difficult stuff, but interesting. All right, so next up we have covalent compounds. Covalent compounds could not be more different because the two elements involved both have very high electronegativity. They both have a low delta En, therefore, that is to say, a low difference in electronegativity, but that's because they both have very high electronegativities. So the individual atoms really want those electrons. So they want to try and take them, but they can't because the other person also wants to take them. So where metals, they're sort of like hippie communes where everybody is really happy to just live together. Non-metals, not so much. They are 1980s shark businessmen, like Leonardo DiCaprio and Wolf of Wall Street and things like that. They are Reaganite guys. They're doing lots of cocaine. They're drunk. I know exactly what I want. I know what I'm going to get. I'm going to own this. I'm going to own this. I'm going to have it spelled out as precisely what I own and how much and who owns how much, and it's going to be spelled in a contract. It's going to be very, very clearly set out. Okay. So they're forced to share because they have to, but they are going to be very clear. So here we have the bonds. Those are the sticks in between the atoms. Each bond represents a pair of electrons, and they can be equally shared, they can be unequally shared between the two atoms, but the result is going to be a sharing of electrons specifically and only between those two atoms. Where the electrons of the metal exist throughout the entire structure because they're free. They run around. They need to grow and learn in their own way. My name is Rain. I'm wearing a dress made out of wheat. Or a dress made out of wheat. Okay. No. These electrons are specifically locked down. They exist only between these two atoms. And this is what gives us the behaviors of these compounds. Okay. Where a metal bond is sort of shared by all the atoms across the entire structure of that piece of metal. For a covalent bond, that bond is only between those two atoms. And thus you build, very specifically, molecules. These little chunks of matter with very different properties based on what atoms are combined in them in what numbers and how they're bound together. So I don't remember exactly what this guy here is. It's some sort of organic compound, a fairly complex organic compound. I don't know what. But, this is a single molecule. The bonds exist between these atoms. They're very specific, very precise. only between those two atoms. Okay? The bonds themselves are very, very strong, okay? But they exist only inside the molecule. Between molecules, from one molecule to the next, you don't have bonds. So those interactions are very weak. So that's what gives us the various properties of covalent compounds. They're soft. Okay, it might not feel like it if you get hit with a baseball bat or you fall on frozen ice. But those weak interactions between the molecules mean that covalent compounds have very low melting and boiling points. Metals and ionic compounds have very high melting and boiling points, hundreds or thousands of degrees. But most of these organic compounds, covalent compounds, until they get like ridiculously huge, they're going to have very low melting and boiling points. So water is a liquid at room temperature. A lot of these organic compounds are gases at room temperature at the same size as water. Okay, so just very weak interactions. Then you have insulators. Okay, I remember movement of charged particles. The charged particles, in this case, still the electrons, and those electrons are all locked down inside these compounds. So they're not going anywhere. If you try, the only way to free up those electrons is to break those bonds, is to destroy the compound, really. You can make pretty art that way, but you would also be not having the compound anymore. And finally, they're dull. Again, remember, color and so on is about light, and that light, those electrons again are locked down. It just can't work the same way. Okay? Again, I'm trying to avoid talking too much about those orbitals. So finally, we have ionic compounds. Okay, so ionic compounds, we're talking about a high difference in electronegativity. So a metal and a nonmetal. One atom really wants the electron, the other atom doesn't. So you get ions of different kinds. One is an anion, that is to say a negative ion, negative ani. And then you have a cation, positive ion. Cats are always positive, even when they're pissed off, especially when they're pissed off. Cats really like being pissed off. It's their raison d'etre. Okay? And so then you have these huge collections, these huge numbers of ions, positive and negative. And then the positive ions are attracted to the negative ions, and the negative ions are attracted to the positive ions. So you get structures. You get these large structures repeating, these complex, beautiful structures of positive ions surrounded by negative ions and negative ions surrounded by positive ions. This here in the upper right-hand corner is the structure of table salt, sodium chloride. You have these small positive sodium ions surrounded on all sides by these by these big negative green chloride ions. Okay, and thus that's what gives ionic compounds their structures and properties. Now, I want to stress, we don't get molecules. Okay, molecules are these guys right here. Covalent compounds have molecules. Ionic compounds do not. We represent both of them with chemical formulas, like H2O for water or NaCl for table salt. But those chemical formulas represent very different things. For a covalent compound, it represents an actual molecule, a piece of matter with those particular atoms. For an ionic compound, it does not represent a molecule. It only represents the ratio of the ions. So sodium chloride, NaCl, represents the 1-to-1 ratio between the sodium ions and the chlorine ions. You are not going to find an individual unit of NaCl. Does not happen. That's something that I think needs to be stressed. We use those chemical formulas in pretty much all of the exact same ways when we are doing, chemical reactions and stuff. But they have very different chemical properties as a result of these very, very different structures, these very, very different bonds. Now, salts. Salt, S-A-L-T. A salt, that's just a general term for an ionic compound. A structure where you have these alternating positive and negative charges. They don't all look like table salt. Some of them are much more complicated. The actual structure of the salt is going to be based on the sizes of the ions and the charges of the ions. So how physically big and how big the charge is. But they're all going to have these similar sets of properties. First off, they're brittle. Okay, so you have negative ions surrounded by positive ions surrounded by negative ions. If you hit this structure with a hammer, you get even just a small shift, right? You get a whole bunch of these things to shift, and suddenly positive ions next to positive ion, or negative ions right next to negative ion, the same really strong forces that were holding that crystal together are now forcing it apart. Okay, so negative is repelled by negative, positive repelled by positive. So salts are very brittle. Okay, you hit them with a hammer, they don't change shape, they just shatter. Next up, these guys have an interesting relationship with conductivity. Okay. Now remember, conduction means the movement of charged particles. There are a lot of charged particles in a salt. There's pretty much nothing but charged particles. However, as a solid, those charged particles are locked down into this structure. They're not going anywhere. They're trapped in place. So a solid ionic compound does not conduct. But if you were to free those ions up so they could move, then you'd get conduction. There's two ways to do that. First, you can melt it. You melt the salt, turn it into a liquid, and it conducts electricity. A lot of elements were discovered in exactly that way. Using the brand new science of electricity, they would just take a random salt, they would melt it, they would run electricity through it, and then they would study the gases or whatever they gave off. Usually highly dangerous, incredibly toxic gases, but still interesting stuff. Or the alternative is that you can dissolve the salt in water. Now, not all salts dissolve in water, but a lot of them do. When they do that, we call them aqueous. That is to say, they're dissolved in aqua or water. That's also when they become an electrolyte. Electrolyte means they conduct electricity. Those charged particles are now free to move in a liquid state or an aqueous state. You apply a voltage, then the positive ions move in one direction, the negative ions move in the other direction. Conduction happens. So those are the three different kinds of bonds, three very different kinds of compounds. You have your metallic compounds that we're not going to talk about anymore after this. You have your covalent compounds, and you have your ionic compounds. You're going to spend a lot of time talking about covalent and ionic compounds moving forward. And with that, we are done with the second set of slides. I'm going to go ahead, take another break, be back in maybe 5 minutes for the next lecture when we're going to talk about predictable